Welcome everyone. This time we are going to talk about Advanced Hydraulics 1. And notice the subtitle here, Who Pays for All That? This is really going to be spent the next hour or so on pipe sizing and how important pipe sizing is. Friction head loss. What we have here is an elbow, picture of an elbow, okay? Remember this, head is our word for energy. So we're talking about energy loss, okay? Friction is a form of energy, it's heat energy. Loss means you're paying for something that you're not getting any use out of. So we're talking about the heat loss as the water moves through the piping system, okay? This should raise an alarm. It should also give you an opportunity to upsell. So we're going to show you how to do some of that stuff. There's a definition for the words deadhead. Remember, head is our word for energy. The definition is when a pump is running against a closed valve. The impeller is spinning, but no water is moving. This creates friction, which is heat. Now, interestingly enough, water is a very good conductor of heat. So that heat will move down the suction pipe and down the discharge pipe to wherever the plug is. Here's the point. If you are using plastic pipe, when the water temperature gets to the melting point of the pipe, notice what happens? Okay, the pipe collapses on the suction side. Why? Because we're drawing a vacuum. On the discharge side, it looks a little different. You'll notice on the discharge side, it swells up. Okay, and that's because we have hot water under pressure. All right, now of course, this is where I give you a safety tip, and my safety tip simply is this. Before that pipe blows, turn the pump off and run out of there. Yes, I said run. And the reason for that is because if you don't get out of there in time, that pipe breaks open, and of course what's going to happen? All that hot water that was in there is going to come through that hole. Now, have you ever heard of water hammer? Water hammer means that you've got weight, you've got momentum, and you've got pressure. Okay? And the bottom line is, when you're moving and then come to a stop, that doesn't mean the water's going to stop. Okay? So the water sloshes this way. Now, water hammer, remember what I said. You've got water moving here. It's got weight. It's got pressure pushing it. It's got momentum to move in a straight line, and someone slams the valve shut. And when they do, what happens? What comes back at you could be up to 6 times what hit that valve. Okay? You develop a lot of pressure in here. Now, got a question for you. What are the 3 factors that make up friction loss? So we're going to talk about friction loss. What makes it up? And so here they are. Notice the title of the slide here, Friction Head Loss Factors. Okay? It includes the type of pipe, the diameter of the pipe, and the length of the pipe. Those 3 things help us to know how much friction loss we're going to have. All right. Now you also have to remember that volume and velocity are tied hand in hand. So as one goes up, the other goes up. As one goes down, the other goes down. All right. Now, of course, the point that we're trying to make here is that velocity is what is going to create friction loss. The faster the water moves through the pipe, the more friction loss I have. So this is a velocity curve. And you're going to notice that the water touching the edge of the pipe, the inside part of the pipe, doesn't move. However, water has a very low viscosity, meaning that the molecules of water can move a little bit faster, a little bit faster, a little bit faster, till you get into the middle of the piece of pipe, and that's where the fastest moving water is. So when we talk about the velocity of the water, we're talking about the speed of the water in the middle of the pipe. Here is a 400-foot length of pipe. It's 2 inches in diameter. All the way through the pipe, the diameter stays the same. Now, I'm going to put 40 gallons in over here. What am I going to get out over here? And of course, the answer is simple. 40 gallons. Where else is it going to go? I got a straight piece of pipe, no T's, no elbows, no laterals, no nothing. So the flow rate stays the same the whole 400 feet. Velocity is going to stay the same. Okay, my flow is going to stay the same. Can't change. Now, remember I said the velocity stays the same, so whatever the speed of the water is going in here, that's what the speed of the water is coming out over here. The reason this is important is there are 3 types of energy in a pipe with moving water that's horizontal. Obviously, the first type is velocity energy. Then there's pressure energy, and the last is friction energy. Okay? Now, understand that if you measure the pressure from here to here at the entrance, you'll notice it's always going to be greater than measuring the pressure from here to here at the exit. All right, remember once we said energy cannot be destroyed or created, it can only be changed. So we're changing energy forms here. Velocity energy always remains the same. Where does friction energy come from? There's only one place, pressure energy. And that's why your pressure energy in is always greater than your pressure energy out. All right? Now, you get some guys that'll say, oh, but wait, if I use 1.5-inch pipe, I'm going to get more pressure. And the answer is no. No, you're not. As a matter of fact, your velocity is going to go up, and so your pressure is going to go way down. And they say, well, I didn't see the velocity line move. And you say, okay, I'll tell you what, let's make you a deal. Here's what we're going to do. We're just going to look at velocity and pressure coming into the pipe. All right, so get rid of all that other stuff, just velocity and pressure. All right, this is the velocity energy coming into the 2-inch pipe. This is the pressure energy coming into the 2-inch pipe. Okay, I add that together. That's 100% of all the energy going into the 2-inch pipe. Now the question is, what percentage is this of this 100%? And of course, most people say somewhere between 20 and 25%. And I just say, okay, whatever. So that means that if I've got 20% velocity, 80% of that energy has to be pressure. All right? Now notice that this is my velocity energy going into the 1.5-inch pipe. This is my pressure energy going into the 1.5-inch pipe. That makes this 100% of all the energy going into the 1.5-inch pipe. What percentage is this of this 100%? And somebody always says 30 to 40%. 30 to 40% more. So the bottom line is, now, if this represents 30%, then I've only got 70% of my energy as pressure energy. Not 80, 70%. So that's where I try to help you to see that your pressure is going to go down as your pipe size gets smaller. If you're going to run the same amount of water through through 2 different size pipes, the smaller pipe is always going to cost you more energy. Always. Okay? Now, remember what we said. We said that water has pressure, it has momentum, it has weight, and it's moving in a straight line. What happens when that water gets to an elbow? And you can see by the picture here what happens is you wind up with all of this hitting that bend, that elbow there. Okay? So, of course, what winds up happening, on the outside edge of the elbow, you're going to have higher velocity and lower pressure. Why? You've lowered the area that the water's moving through. On the inside of the elbow, because you don't have as much water, your velocity is going to go down, which makes your pressure go up. Okay? Now, this is the friction loss table. It is in the Stay Right condensed catalog, page 152 and 53. It's in the Berkeley condensed catalog, I believe it's page 170. And in the Myers catalog, it's page 89. So it doesn't matter which condensed catalog you have. If you've got one of our condensed catalogs, you've got a friction loss chart. Now notice that if you're looking on the page there happens to be 7 charts. The upper left-hand corner says 1/2 inch, then it says 3/4, 1, and 1 1/4. You go to the second grouping, which is either below it or next to it, and you're going to see it says 1.5 inch, 2 inch, and 2.5 inch. Next to the 2.5 inch chart, it says note, recommended velocity is 5 feet per second with a maximum of 7 feet per second. So we're going to really, really encourage you to keep the velocity below 5 feet per second. We'll let it go to 7 if you want to, but I'm going to show you what happens when you do. 2 feet per second. That's all that it takes, 2 feet per second, to double your friction loss. All right? Now, when you look, there are 7 charts here. When you look at each one of those charts, there's 5 columns in each chart. The first column says flow in U.S. gallons per minute. So what this means is you can't just look straight across the page. You've got to look at each individual pipe size to find the flow rate. Velocity, it's a little bit misleading because it says plastic and then it says feet per second. Now, what makes it a little bit misleading? The fact that velocity is velocity. Okay? As long as the pipe ID is the same, the velocity is going to be almost identical. All right? The next column says plastic pipe has a C value of 140 and an ID of 0.622. Your steel pipe has a C value of 100 with an ID of 0.622. You notice the IDs are the same. Then you get to your copper pipe. It's got a C value of 130 and an ID of 0.625. So they're all really, really close with ID, which means the velocity is going to be really, really close. Understand that the plastic pipe they're talking about here, this is an extremely important section, so make sure you're listening now. The plastic pipe they're talking about here is Schedule 40 PVC. Remember what happens when you go to Schedule 80 or Schedule 120. The wall gets thicker, the ID gets smaller, and the friction loss goes up. Okay? Now, remember what we're trying to teach you here. Keep the velocity within 5 feet per second. If you really have to, we'll let you go to 7. So, if you look down column number 2, I took the number out. What number belongs in that box right there? What's the velocity? How close to 5 feet per second can I get without going over it? If you said 4.8, you got it right. Okay? Now, of course, at 4.8 feet per second, my flow rate is 4.5 gallons a minute. The other thing I want to point out is my friction loss in plastic pipe is 18.3. 18.3 feet of head loss. How many pounds of pressure is that? So we take 18.3 times 2.31 and we get 7.92. We'll call it 8. Okay? Now, here's the point. Here's a 100-foot length of pipe. Okay? Schedule 40 PVC. 1/2 inch. We're going to put 4.5 gallons in, and of course we're getting 4.5 gallons out. I want 50 psi on the outlet. What pressure do I need to put in on the inlet? And the answer is 58. I'm going to lose about 8 psi going through this piece of pipe. So that means I need to put 58 in so that by the time I get 100 feet down the line, I still have 50 psi left. All right? Now, if we look at the chart, how close can I get without going over 7? 6.9. What happened to my flow rate? It went up 2 gallons a minute to 6.5. So I take that same half-inch Schedule 40 PVC. I change the flow rate to 6.5. My velocity goes up to 6.9. Look what happens to my friction loss. Almost doubled. I went up 2 feet per second, and I almost doubled my friction loss. 36.2. Here's that same 100-foot length of pipe, half-inch Schedule 40. We're putting 6.5 in over here. Went up by 2 gallons a minute. We're going to get 6.5 out over here. I still want 50 psi. Now I have to put in 66 because I'm going to lose almost twice what I did before. Okay? Now, if you think that's bad, take a look at steel pipe. 67 feet of head loss. Okay? So we're going to get rid of the plastic pipe. We're going to put steel pipe in. We're still going to put 6.5 in. We're still going to get 6.5 out. We still want 50 over here. Watch this, though. I have to have almost 80 psi. 67 feet of head is almost 30 psi. So I have to have a total of 80 just to get through that 100 foot of pipe and still have 50 left. And think of it this way. What would happen if I had to go 300 feet? Now I need 90 psi just to get through the piping system. So you can begin to see how important friction loss is. Okay? So, I want to point something else out here to you. It has to deal with both friction loss and velocity. If we were to put 200 gallons a minute through 2-inch PVC, the velocity in feet per second would be 19.1. All right? Double your pipe size, you're really quadrupling your area here, and you'll notice you drop your velocity by almost a quadruple to 5.11. Now, if we go over to steel pipe, our velocity goes a little bit less even, 5.05. Now, of course, 6/100ths of a foot per second, I don't think there's anybody that's going to be able to just look at that and see that, oh, yeah, we got 600 foot per second difference there. Okay? So since you're not going to be able to look at it and see that, I want you to know we're going to say they're the same. Close enough the same, we're not going to worry about it. But look at your friction loss. Friction loss in steel pipe, 4.3. Friction loss in the exact same size plastic pipe, 2.06. Now, I got another question for you here. This question says, what makes up total suction lift? Remember, total suction lift means we're looking at the suction side of the pump. And so we're going to look here. This problem is going to help us to learn two things. One, how to calculate friction loss, and two, how to calculate total suction lift. So we have a pump sitting on a pier. By the way, this takes place in South Carolina. It's based on a true story. We've got a piece of pipe going down into the water there. The piece of pipe, equivalent piece of pipe here, is 10 feet. Okay? We are 4 feet off the water. All right? Now, in order to calculate friction loss, there's 4 things you need to know. You need to know your flow rate, so we're doing 20 gallons a minute. You need to know the size of the pipe, we have 1.25 inches. You need to know the type of pipe, we have PVC, and you need to know the total length of the pipe, we have 10 feet. Okay? So the first thing we're going to do is we're going to look at the friction loss per 100 feet of pipe. All right? So 20 gallons a minute through 1¼ PVC has a friction loss of 6 feet per 100. So I'm going to lose 6 feet per 100 here. Okay? I have 1/10 of a 100-foot length of pipe. So I take 1/10 times 6 feet per 100, and I wind up with 0.6 feet of friction loss. My vertical distance was 4. My friction loss is 6. So my total suction lift is 4.6. Okay? Now, I want you to understand this based on a true story, and what happened was, over the time of the next 3 years, that lake dropped a total vertical distance of 6 feet, making my vertical distance here 10 feet. And I want you to know there's only one way to overcome vertical lift, and that is to physically move the pump closer to the water. Now, can you imagine what's going to happen, though, if the water comes back when you're not around? You now have an above-ground pump that is submerged, and they don't work very well that way. Okay? So, we have to leave the pump on the pier. We have another problem, however, though, too, and that is that there is no water around that pipe at all. So we've got to extend the pipe not only down to the water, but far enough out in the water that will be at least 6 times the pipe diameter below the surface of the water. So that way we don't whirlpool. Okay? That makes our total length of pipe 100 feet. All right? So if we use the 1¼ pipe we were using before, our total friction loss is going to be 6 feet because we're going to lose 6 feet per 100. Our total suction lift now, 6 feet plus 10 feet is 16 feet. Can we save some of this lift? Can we change it so we don't have 16 feet? And the answer, of course, is yes. That's why I brought you here. So what we're going to do is we're going to upsize that pipe from 1¼ to 1.5. With 1.5 pipe, our friction loss is only 2.83 per 100 feet of pipe. So if you take your 2.83 plus your 10, now your total suction lift is only 13. Do you see what happened there? We went up 1 pipe size and we saved 3 feet of head. Can we do better? Well, let's check it out. Let's put 2-inch pipe in. 2-inch pipe has a friction loss of 0.839 per 100. So now our total suction lift is going to be 10 plus 1, or 11 feet. Now, do you see what we did? We saved 5 feet of friction loss. 5 feet is 1 box chart in my box chart charts. Okay? So I can move over 1 column in my box charts because I went up 2 pipe sizes here. Can we do better yet? Let's check it out. Let's go to 2.5-inch pipe. 2.5-inch pipe has a friction loss of only 0.353. All right? So now our total suction lift is going to be 10 plus 0.353. We'll call it 11. Did it really make any difference to go up another pipe size? And of course the answer is very obviously no. It did not. So what do we learn from all this? Now notice the wording here. 2 times the pipe size larger than the pipe size at 5 feet per second makes fractional pipe sizes most efficient. What do we mean by fractional pipe sizes? Half, 3/4, 1, 1 1/4, 1 1/2, 2, 2 1/2, 3, 3 1/2, and 4. I want you to understand that this next problem is going to be looking at a different side of it. We're going to be looking at velocity. Okay? So, 1-inch pipe at 10 gallons a minute. What's the velocity? And if we look it up here, 1-inch pipe, 10 gallons a minute. Velocity is 3.7. So we'll put 3.7 in there. Now, if you take the same 1-inch pipe and you put 20 gallons a minute through there, same thing here. 20 gallons is 7.4, so we'll put 7.4 in there. And what do we notice between the velocity numbers and the flow numbers? Yes, they're doubled. They're doubled. And that's just the way that it is. If you double the flow, you double the velocity. And you need to remember that. All right? Now, this is in the Water Systems Training Manual. And it says that if you use 3/4 inch pipe, and by the way, I went through and made this up myself, you can put a maximum of 8 gallons a minute through there and stay under 5 feet per second. 1-inch pipe, 12 gallons a minute. 1.25 inch, 20. 1.5 inch, 30. 2-inch, 50. 2.5 inch, 70. 3-inch pipe, 110 gallons a minute, keeps the velocity below 5 feet per second. If you want, I have a ruler. Just email me and I'll get you the ruler. All right? And you'll notice the ruler has 6 inches there. It has inches of mercury here, and it has feet of head there. Now, what does that mean to you? It means the suction side of the pump. I put a vacuum gauge on the suction side of the pump, and the vacuum gauge reads 21 inches of mercury. What does it mean to me? Almost 24 feet of head. 23.79 it says there. Okay? So that means that my pump thinks I'm lifting the water from almost 24 feet. I get a tape measure out and I say, you silly pump, you're only 3 feet off the water. Why is it reading 24 feet? It's one of two things. It's either a plugged suction or it's an undersized suction pipe. To get that much, I'd say probably it's a plugged suction. Now, flip the ruler over and you'll see that it says pounds of pressure, feet of head. This is the discharge side of the pump. I used to keep this side taped up to my wall in my customer service, so when someone called in and said, I need 50 PSI, I'd just glance at it and say, that's 115 feet ahead. And they'd say, wow, you're really smart. And I'm thinking, yeah, I'm smart. I got my ruler taped up here. Okay? Now, the most important reason for giving you this ruler is right here. It says pipe size. It starts out at 3/4 inch. It goes all the way to 8 inches. I went through and I found what the flow rate was in that size pipe to keep the velocity below 5 feet per second. So, of course, 3/4 inch is 8 gallons a minute. 1 inch is 12. 1.25, 20. What if you were looking for a customer who wanted 40 gallons a minute? What size pipe would they use? Well, 30 is 1.5 inches. 50 is 2. You have to go with the 2-inch pipe. It has to be above the flow range that's there. So, all right? Now, we're going to do a couple simple problems here. The first one says, let's take 1.5 inch pipe, plastic, 25 gallons a minute, and the total actual length of pipe is 235. Now, that includes the linear feet of pipe plus any fittings that there are. Okay? So, what's the velocity? First question you always want to ask yourself. All right? If you look it up in the book, Stay Right, Berkeley, Myers, doesn't matter, it's 3.9. What is the friction loss per 100? 4.26. What do I divide by here? I divide 100 into 235 to find how many 100-foot lengths of pipe I have, and I have 2.35 100-foot lengths of pipe. Now it is simply a math problem. 235 times 4.26 equals 10. 10 divided by 2.31 is the equivalent of about 4.3 pounds of pressure. So in this particular problem, over the span of the 235 feet of 2-inch pipe, remember some of this is not actual pipe, I'm going to wind up with a total friction loss of 4.3. Now, just to make the system easy to understand, we're going to do the exact same problem, with one exception. We're going to make it 1.25 inch pipe. So what's the velocity 1.25 inch pipe at 25 gallons a minute? 5.4. It's greater than 5 but less than 7. Let's see what it's going to cost us. Okay? So the friction loss per 100 feet of pipe now goes to 9.06. So everything stays the same, playing 9.06. I still have 235 feet of pipe. That leaves 2.35 times 9.06 or 21.29. So for you divide that by 2.31 and you're going to get about 9.2. So you're going to notice what happened here. We went down one pipe size and our friction loss more than doubled. And that's what you have to kind of watch for. Okay? So here is the friction loss through fittings, and notice what it says in terms of equivalent length of pipe. Remember I said that total length of 1.5-inch pipe or 1.25-inch pipe was 150 feet. Okay? Well, 235 feet. Remember I said that total length of pipe was 235 feet. And I said it included equivalent length for fittings. So here's what we're doing. What we're really doing here is we are going to take this elbow, this 90-degree elbow, and you're going to notice that we're going to turn it into a straight length of pipe. Okay? So the way that we do it here is we've got the elbow, and it's going to equal 7. We've got the standard T, it equals 12, and we've got the gate valve, that equals 5. Okay? But more importantly, I want you to note, plastic pipe, which has the least amount of friction loss of all the different pipes, has more friction loss through the fittings. Okay? Now, we're going to work this problem out here. We've got 1.25-inch pipe carrying 20 gallons a minute, 275 feet with these fittings. Okay? 275 feet. That's the straight pipe. We've got 3 standard elbows here. One standard elbow equals 7 feet. 3 times 7 is 21. We have 2 standard T's. A standard T equaled 12 feet of straight pipe. That's going to be 24. We've got 1 gate valve. It equals 5. So there's 5. Remember, we're going to leave it open as much as possible. And now we add this all up. 21 plus 24 plus 5 equals 50. So we've got 50 feet of equivalent length of straight pipe. Now what we do is we take that 50 feet of pipe and we add it to our actual length of 275, giving us an effective length of pipe of 325 feet. We divide that by 100, and that's 3.25 100-foot lengths of pipe. The friction loss per 100 through the 1.25-inch pipe is going to be 6 feet per 100. So we now take this 6 feet times our 3.25, and we wind up with 19.5. 0.5 times 6 is 3 feet of head loss. If I take just the fittings, I had 50 feet of pipe, so that's 0.5 100-foot lengths of pipe times the 6 feet is 3 feet of head loss. All right? 3 feet is a smidge over 1 psi. Am I going to worry about 1 psi? Probably not. Our total loss was 19.5 minus the 3 leaves us 16.5 feet of head loss in the 275 feet of straight pipe. Okay? Now, I'm going to round that up to 17. I'm going to take 10% of my friction loss. So 10% of 17 is 1.7. I'll round that up to 2. 2 and 17 is 19. Did I get close enough to my 19.5 feet? And the answer is yes. Is it always going to be this convenient? And the answer is no. It's not always going to be this convenient. But this time it did work out that way. Okay? Now, this is all based on one very important factor, and that is that we have less than 9 elbows. Why? Because according to plumbers, 9 elbows equal a plug. So, if there aren't any questions, We're going to move on to the next topic then. I really appreciate you being with me. I hope you'll be with me next time. We look forward to it. Thank you so much and have a great day.